I gave this talk the title, How to Look Like a Statistician. So your first reaction might be, but I don't want to look like a statistician, because statisticians are not actually famous for being very cool or trendy. This is actually a very famous statistician, David Cox. He did quite a lot on survival models, so we can do model on if you will survive this talk or not. So, as I mentioned, statisticians are not famous for being especially fun or trendy, but probabilistic programming is something that's used a lot in statistics and a lot in machine learning. But to look like a machine learning researcher is a bit too long. So, I actually did some search in stock photos to see how a mathematician should look like. So this is one stock photo that I found. I like two things about this photo. First, the person is wearing a lab coat. I don't know, mathematicians don't really wear lab coats. And the second one is that he's writing on the glass, basically in reverse. So this is how you will look after this talk, probably. Sorry. So, let's talk about probabilistic programming, what it is actually. I don't know if you have ever heard about probabilistic programming, but this is one stream in machine learning that's gaining quite a lot of momentum right now. Probabilistic programming, and how does it even relate to functional programming as well? And something that works. Well, I don't want to dive too much into mathematics first, so first I will have to talk about probabilistic models, because probabilistic programming is actually a way to do inference in probabilistic models. But what does it mean to actually create a probabilistic model? I will show you some practical example of that. I was playing with some data from the Stack Overflow developer survey from last year, and they were asking about a lot of things. Who filled in the developer survey? Oh, quite a lot of people, so you probably know what it's about. They ask a lot of things about what languages you use, what languages would you like to be using, more functional of course. If you are using certain technologies, where do you live, and what's your salary. And last year they were also asking about tabs and spaces, if you use tabs or spaces. And they found that there is an interesting correlation between high salaries and using spaces. That doesn't mean causation. So I was looking at the data they gave them for download, and I looked at salary distribution altogether. These are salaries that people reported worldwide in dollars per year. And this is just a histogram of the people, and I noticed that this looks a little strange. Why there is like a bunch of people in the middle who have salaries around $50,000 per year, but there is quite a lot of people in the beginning, near zero, that are reporting very low salaries. So I was thinking, okay, that's interesting. So I split it based on some countries, and I looked at countries where developers report very low salaries, the ones around zero. The most common ones are from India. That sort of makes sense, unfortunately, because in India the pays are not that large. But the second one is Poland. What's happening? Do you guys earn very little? But these are developers who report their annual salary below $3,000. That's very little. You wouldn't be able to live in Poland on such a salary. I'm from the Czech Republic, and the salaries are similar, so I can imagine. And the third, where developers report very low salaries, is Russia, and then Brazil, okay, Romania, Pakistan, Ukraine, and Germany. This is weird. I work as a data scientist, so I looked at it and thought, okay, this is really weird. I would expect India to be there, I would expect Pakistan to be there, but Germany? So I decided to dive a bit more into the data, And here I plotted distributions, estimated probability densities of salaries from France, India, and the UK. And you can see that these are mostly just one peak distributions centered around the different numbers because the salaries overall are slightly different. And in the UK, the salaries were the highest on average. Then France was a little bit lower, India was a lot lower, but you can see a nice bump there. So then I looked at Poland and Russia and Germany. And you can immediately see that there is something happening there because the bumps look very different. For Germany, there is one big bump and one small bump before that. For Poland, there are two more or less equal bumps. And for Russia, there is one bump at a really small value and then smaller bump later. So I thought, okay, I think I know what's happening. So what's wrong with the data? Why are there groups of programmers that are seemingly earning very little and then a bunch of programmers that are earning more? Well, I looked at the question that they asked in the survey, and it was, what is your current annual salary in your local currency? Please enter a whole number in the box below without any punctuation. If you prefer not to answer, please leave the box blank. They underlined the annual. But my suspicion was that probably quite a lot of people don't read questions properly. They feel, okay, salary, okay, bang, I'll put in my salary. And I asked a couple of my friends in Poland, and they all confirmed my suspicion that in Poland, if you are negotiating your salary or if you are talking about your salary, you talk only about the monthly value. In the UK, in the US, everyone talks about their yearly salary. But in Czech Republic, in Poland, I assume in Russia, in Germany, everyone talks about their monthly salary. So people just glanced at the question, okay, my salary, and bam, they put in their monthly salary. So that's my suspicion. And I will try to estimate that later in my talk. So this is actually zoom in onto Poland. So I actually looked at it and I calculated what's the small bump, what's the bigger bump, and really the small bump seemed to be about 10, 12 times smaller than the big bump. And I will look at how many people in Poland can't read questions properly. Just to have something proper to work with. So my theory is that people reported their monthly salary. How do I formalize that as a probabilistic model, and how do I compute that using probabilistic programming? Well, I will have a look at something called mixture distributions. Because you saw that there are two bumps, and there are some standard probability distributions, but none of them really has two bumps. So I have to do something called a mixture distribution, where I will take some standard distributions and put them together to get one distribution with as many humps as I want. So this is an example of something called a mixture of Gaussians, where I have two probability distributions, one is in red, one is in blue, and right now they have equal values, and these are the original distributions. And if I do a mixture of them, I will just get a composite distribution that uses these two distributions as their parts, and I get the total value. And I can change the weights, and that will change how large the bumps are. So this is taking 0.2, 20% of the first distribution, and 80% of the second distribution. And this is when I do it the other way. You can see that the bumps change sizes. So I can use this to fit my salary data. And now you might be thinking, okay, why are we talking about these distributions? I didn't come for a statistics class. Well, that's what probabilistic programming is about. Sorry. So, probability distributions in probabilistic programming become basically first-class citizens in the language. And you can use any kind of manipulations on them. And if I do this a bit more formally, because you can't really avoid mathematics, my assumption is that salary will be the probability that someone couldn't read the question properly, or could read the question properly, times one normal distribution, plus probability that someone couldn't read it properly, times the same distribution divided by 12. And this is mainly to scare you, because I don't really want to do these kinds of computations and write down all the probability distributions and things like that. So, what can I do instead? Well, one thing that's very used in probabilistic programming and any kind of statistics where you are dealing with complicated probability distributions is called sampling. And in a lot of probabilistic models, you can't really compute values directly because the distributions are really complicated. I had just 2 Gaussians and 1 probability that someone can't read a question. But if this gets much more complicated, then you have to do something called sampling, as I said. And just to show you an example of sampling and how it can be used to infer probabilities directly, do you know the Monty Hall problem? Have you heard about it? Yes, some people are raising their hands, some people are shaking their hands. Do you remember the solution to the Monty Hall problem? That's the question. So, the Monty Hall problem comes from a US competition called Deal or No Deal. And it ran in the 70s. And there you had 3 doors. And the Americans came there dressed as crazy as they could, basically. And they could win a car. This is a nice Chevrolet from the competition. And the idea behind the competition was that you have, well, this is a simplified model of the competition. And it's called Monty Hall because the moderator here is called Monty Hall. So you had 3 doors, and behind one of them is a car, like a nice 70s Chevrolet or something like that. And behind 2 other doors, there are some things that don't have any price, and in the Monty Hall problem, these are goats. So maybe someone wants to win a goat, but you are supposed to win a car in this competition. And the idea is that you have these 3 doors, and you pick one. And then Monty Hall opens one of the other doors and shows you that there is a goat. And now the question is, should you switch your choice or not? Who thinks you should keep your original choice? Does it matter? Does it not matter? And should you switch the door? Majority of people would switch the door because they know the problem. So, and they don't want to win a goat. But you can either now write down all the probabilities and compute, use the Bayesian theorem, conditional probability, and compute the actual probabilities. But this is quite hard to get right, because when this problem was originally asked in a magazine, a statistician answered, okay, you should switch the door because of this and this. And they got hundreds of thousands angry letters, even from scientists and mathematicians, saying, no, this is wrong, because it doesn't depend on what does it change if you switch the door or not, because you picked it originally. Well, you might have heard about Erdős, which was a famous Hungarian mathematician, and he only got convinced that you should switch the door after showing them some simulations. So, let's do that. Here I have a very simple program in F# to do the sampling. So behind every door is either a goat or a car, and the game is just some list of doors, and I can either stay with the door I picked originally, or I can switch the door after the goat is shown. So let's actually run things. Let's generate some game. And now here I have a little function that will play the game, where I will first choose one door, then Monty Hall will open some other door that hides a goat. And then if I decide to switch, I will switch to the other door, otherwise I will keep the door that I currently have. So let's run this. And I will run this 100 times. And now it tells me that if I stay with the original door, my probability of winning is 0.35, and if I decide to switch the door, my probability of winning is 65%. So if you haven't seen this problem before, this might be counterintuitive. I think the best way to think about this problem is that originally when you are picking a door, you don't have any information about which door contains a car. But after Monty Hall opens one of the doors that hides a goat, then suddenly you have more information about the other door that you haven't picked. The information about your current door that you picked stays the same, because you had probability of 1/3 of winning the car originally. But when you switch, you are switching to a door that you have more information about. But I want to talk about other things. First of all, here I did 100 samples. If I do 10 samples, my estimate will be more off. My estimate that I will win a car if I stay is 40%, and if I switch, it's 80%. If I make more samples, my estimate will be more precise. So now if I stay, my probability is 34.9, and if I switch, my probability of winning is 68.1. And if I do even more samples, it should approach the theoretical value, which is 33% and 66.6%. So as I'm adding samples, my estimates are getting more and more precise. And I'm basically just sampling directly from the probabilities. And this is something called Monte Carlo sampling. If I have the situation that I want to know about, I just sample directly from it and get the probabilities. This is a very simple scenario. If you look more into probabilistic programming, you will come across something called Markov chain Monte Carlo, which is an additional layer of complexity above the Monte Carlo sampling, where you don't have the probabilities directly, but you sample from things and you gradually approach the probabilities that you are interested in. So this is Markov chain because it's chaining the probabilities together and getting to something that you actually want to sample, that you don't have access to directly in the beginning. But here we had access to the probabilities directly, so we could do just direct Monte Carlo. So can we do something like that for our mixture distributions? As I was showing you, we get a mixture distribution, like the ones I was showing, using some normal distributions that have some mean and variance, and some mixture proportion, the probability that someone can't read a question correctly. So sampling from this situation is very easy if we knew all the parameters. If we knew the values of the means, what's the average salary for the person who answers the question correctly, what's the average salary for the person who can't answer it correctly, and what's the proportion between these two. But I don't know the actual values. So I will have to do it slightly differently. I will first have to infer the parameters. And this is something that you can do once you have something called a probabilistic programming language. All I had was that salary is some kind of Gaussian that I'm interested in, and the probability of a mistake is basically a probability that's between 0 and 1. You can imagine it as a coin toss. Okay, can someone answer the question correctly, or can someone read the question correctly, yes or no? And using differently biased coin, and that's something called the Bernoulli distribution, because statisticians can't call it a coin toss distribution. It's Bernoulli to look more fancy. And my observed value, then if someone made a mistake, then I will just divide the salary by 12, and if someone answered the question correctly, I'll just take the salary directly. This is basically how we can sample from the distribution, because now, if we had nice probabilistic programming language, we write this, and then the compiler does everything behind the scenes, because it knows what distributions do variables have, and I can operate with them directly. So if something is a mistake, that's a sample from the distribution. And the salary is a sample from the distribution as well. And then my probabilistic language will give me estimates, okay, what's the mean, what's the variance, or I can do more computations afterwards. So here you can see two things. First, I'm just using the distributions directly. I'm not actually writing out how to sample the values from the distributions. And second, I can then manipulate the values as if I had them directly, even though they are samples from the distribution. So let's have a look how we can actually do something like this. And I have a very simple implementation here in F#. Here are some helper functions. Now I have a few types. I have the type for the distribution value, and my samples will be a float, so that's a float. And then I have two distributions that I'm interested in, and that's a Gaussian with some mean and variance, and a Bernoulli, which is some probability. And now this gets more interesting, because I will have almost a monad here. So here I have a slightly more complicated type for probabilistic computation. And if I have a distribution and I want to do some computations with a distribution, well, I can either take a sample from the distribution or do something with it, sample it behind the scenes, and then continue with the computation. Or if I have some value, I can just return the value. And then I will use, if you know F#, this will be a computation expression where I just return, define the return and bind values, and define my computation expression here. And now this model is basically the thing I was showing you before in the slide. So now my probabilistic model will be wrapped in my probabilistic computation. And I will just take the yearly salary. I will take the probability that someone made a mistake. And now, like I was showing you in the slide, I can just directly manipulate with the values from the distributions, even though these are samples somewhere behind the scenes. So here I basically just go into the distribution, and I can either sample and then continue with the computations, with the Bernoulli, with another sample, etc., or I can just take the value. So this is my program that I can just run if I implement all the other bits behind that. So how do we actually do the sampling for the mixture distributions or for more complicated distributions? How do we get to the values of the parameters if I want to estimate them? Well, that's simple. You just define the proper distribution and then you just write down how to sample from it, right? It's easy. Well, these are actually screenshots from my PhD thesis, because this stuff is really hard. And I got a PhD from Cambridge for it. So this stuff is hard and you don't want to do this. You really don't want to do that. And that's why probabilistic computing is a good idea, because this basically abstracts all of this. You leave this to the programmer, to the author of the language, and it's done in the compiler, basically. All this complicated stuff, all the equations, sums, integrals, everything. Because that's what probabilistic computing does. Just write down your distributions, write down what you want from them, and bam, everything is done. So I will show you in the program, I implemented the world's slowest probability inference engine that I will create to use my slowest probabilistic programming language. Because what you can do if you are really, really lazy, you just want to know which parameters are the most likely to generate the data. So you can go through all the parameters. You can examine all the possible means, you can examine all the possible variances, you can examine all the possible values. In my case, I have just 3 parameters. I have the mean salary, I have the variance of the salary, and I have the probability that someone made a mistake. And it's already taking ages on my laptop. So you really don't want to do this. This is a really bad idea. But it will show you how you can then abstract it and basically leave it up to the compiler to do all the ugly stuff somewhere else. Because in real probabilistic languages, I was showing you the computation expression before, and what this gives me is complete control over the execution of the probabilistic program. And the real world probabilistic computations, they usually involve derivations and differentiations of the programs. And this is very easy to do if you have an AST of the computation, and this is what you can get in functional programming or functional languages very easily compared to something more complicated. So there is, for example, probabilistic programming language written in Clojure called Anglican, which is also quite popular, and it operates on very similar principles, just more complicated because you don't have to deal with all these things. So, as I was saying, I will do a complete enumeration, but I'm dealing with continuous distributions, so I will basically just discretize everything. This is my histogram of salaries, so I will basically take all these bins and treat them as number of observations in each bin. And I will do the same for the theoretical distributions, for the original Gaussians, where I will discretize them and look at the percentage of the value that fell into different bins. And then I will just compare the two. So, the slowest probabilistic language ever. So, what I'm doing here is that I basically just vary the parameters and get all the possible parameters that I can get for my Gaussian and Bernoulli distribution. And this is a discretization. And here I will just basically enumerate all the possibilities and vary all the parameters. And then I will compute the histograms for all my probability distributions, the theoretical ones. And you can see that even though it's fairly easy, there is quite a lot of code involved. And here is my function to actually compare the histograms and compute the most likely distribution. So I will just run everything I have here, and you'll see that it already takes quite some time because it's calculating the discretized theoretical distributions for all my possible values of parameters. And now we wait and wait and wait. That's actually fairly typical when you are dealing with any kind of probabilistic language because these things are slow. Even though you might have very efficient implementation, it usually takes a really long time on real-world problems. In my PhD, I had to implement some of this stuff myself, and it took weeks to compute. And I want to run it on the Stack Overflow data. So I'll just load the actual data. Some things I wanted to mention. You usually don't work with the probabilities directly, but you work with them in logarithms, because otherwise you'll have to compute products of a lot of probabilities, which will get really, really small very easily. So in my first attempt, I was getting probabilities 0 for everything, because it just went really, really low. So you work with them in logarithms, because then products of probabilities turn into sums of logarithms. So I got my Stack Overflow data loaded, and let's get the results. Let's pick the most likely distributions that generated the data. So now it's basically just it created a histogram from my values that are observed, and it's comparing them with all the possible combinations of values in the theoretical distributions. So now it tells me that the most likely value, this is the log of the probability, so I'm getting a very small value in negatives. The probability that someone made a mistake is 25%, so that's quite a lot. And this is the distribution of salaries in Poland. So this is the mean, it's $24,000 per year. And this is the variance, and if you take the square root of variance, you will get a standard deviation, which tells you that if it were a normal distribution, that about 97% are plus or minus 3 standard deviations from the mean. And now you're thinking, oh, what's that? This is how it actually looks. So this is my estimated distribution of salaries in Poland. I was looking at this and I was thinking, okay, maybe there is another source of mistakes in the data as well, because do people generally talk about their salary before taxes or after taxes? There's nothing about it in the original question, so I think that's another source of noise in this. But this is my estimate. If I try to fit 2 Gaussians to the data that I was showing you before, this is how it looks. And my amazing probabilistic language gave me the most likely distributions. But really, you could see that there is quite a lot of work involved to actually get the probabilities right, etc. But all I want to do when I'm actually dealing with something like this is to write the setting, write the model, and not align more, because then the probabilistic language will just take care of the rest. So, how does something like this look in the real world? Unfortunately, there is no probabilistic language written in F#, but what I'm using at work quite a lot is called Stan, it's written in C++. I'm sorry, I'm not actually using Clojure and Anglican, although I should. There's also one language written in JavaScript, etc. But this one is fairly efficient for real-world cases. And here you can see this is just my model specification, where I was actually modeling more groups than just 2 with probabilities of mistakes. And these were like prior probabilities for my normals. And it's a bit uglier than my formulation before, but this is how it looks in the real world. And all I need to do is to just specify the model, specify what distributions do individual variables have. And because I was writing this in my statistician persona, I was using Greek names for all variables, because that's what statisticians do. And then I can just use it by compiling the model. It compiles it into C++, and then just run sampling. That's all I need to do. I won't be actually running it here, because we would be here for a bit. But this is how it looks in the real world when you actually want to use it on something practical. But I hope you can see that here I'm just basically defining distributions of variables and then just giving some data and running the sampling, because I don't want to do that myself. So, that was my slowest ever probabilistic inference engine. And now I think we have 10 minutes for questions. Thank you. So, I hope you are looking like this right now. So, anyone feel like they want to write some probability distributions and run some probabilistic programming now?
Hi, I had a question about you generate your probabilities from the samples.
Yes.
Then, do you have to write a metric for for saying how close it is to the histogram data? How do you decide how close you are?
How close are the histograms from each other?
Because you afterwards want
the
to rank
real
them by
data compared to the theoretical distributions. Well, what I did, when I have a histogram like this, I can treat this as something called a multinomial distribution, which is basically just the distribution of values. If you have a set of discrete categories, how probable it is that something will fall into that bin, into that bin, into that bin. So my coin toss distribution is a simplified version of that for only 2 categories. How probable is it that someone makes a mistake or doesn't make a mistake? And once you have a distribution like this for, let's say, 100 different categories, does the salary fall into $0 to $1,000, $1,000 to $2,000, $2,000 to $3,000, etc. Then you can use this multinomial distribution, actually compute how likely is it that you will see 5 observations in the first category, 10 observations in the second category, 15 observations in the third category. And you do that by, you can just go to Wikipedia, multinomial, and you get this by looking at the probability mass function. and you basically just compute this thing. Oh, sorry. And you can do it in logarithms, so you just take number of observations times logarithm of the probability, and you sum it across all the data. And this is how it looks in code. Okay, so here I basically took all the data. This is my function to compare data histograms. Sorry. I basically take probabilities for each bin, and here I fold it over the data where I'm just taking the observations x and multiplying them by the logarithm of the probability and summing it over all the data. So this is the probability that 10 people reported their salary in this range, 12 people reported their salary in another range.
Okay, thanks.
So this is a principled way to compare two histograms in a probabilistic way. But as I said, if you actually want to do probabilistic programming, you don't have to care about this.
Okay, good.
Another question then?
I would have...
Sorry.
Yeah, there are only 2 microphones. Sorry.
I would have 2 very short questions,
Okay.
one technical, one slightly less technical. Do you consume stan from R because it is too hard to consume it from F sharp too?
Do I consume stan from R because it's too hard from F sharp? No, it's because I didn't write a wrapper in F sharp yet, maybe.
Okay.
Because the wrappers around stan are from all different languages. There is one in R, Python, Java, Scala. I should write one in F sharp, but I didn't yet.
Okay, first. And the second is that in your model, did you use Gaussian for the sake of simplicity? Because it has one less parameter, because none of the payment distributions look like Gaussians at all. They are all long tail distributions.
That's actually a very good question. Why did I use Gaussians? Because they are easy. Normally, if I was doing this in the real world, I would use the gamma distribution. It has 2 parameters as well, shape and scale. This is how it actually looks. And you can see that this models the salaries a bit better, because it starts from 0 and goes to infinity. The bad thing about Gaussians is that they are symmetric, so even for my observed data, if I go to my final distribution, it assumes that the salaries go into minus as well, into negative values, which doesn't happen in the real world. But I can say I did this on purpose, because in any kind of, if we are dealing with probabilistic models, you quite often see people using Gaussians, even though the data are not really Gaussian. And that's because Gaussians are easy to work with. Yeah. Negative salaries, well, I don't know if someone in Poland reported negative salary though. So I would normally use a different distribution, but I thought that everyone is familiar with Gaussians and I didn't want to add another layer of confusion. But the thing is, Gaussians are quite easy to work with and they are not that bad. If I look at the estimated, this, if you close your eyes, it looks a bit like a Gaussian. Yeah, you can see here in the UK, this is more or less, yeah, it doesn't really fit a Gaussian very well. It would be more sort of the gamma distribution. But gamma for larger values of scale and shape parameter are fairly close. You can approximate that. And as I said, Gaussians are easy to work with, and a lot of people use Gaussians where they shouldn't. So, me included. Any other questions?
I have a question, because you proposed a model with 3 parameters, and I've seen in the table the parameters could change a little without almost no changing the goal function. And my question is about confidence intervals for the parameters. Are you able to find them?
If I was looking for confidence intervals, I wasn't looking for confidence intervals in this case.
But in general, in such a model?
In general, I wouldn't be looking for confidence intervals because I'm a Bayesian statistician. I don't want to go into this whole debate of Bayesian statisticians and frequentists who are looking for confidence intervals. I'm looking for the complete distribution. And if I have the complete distribution, I don't need confidence intervals because I know how the complete distribution looks. I don't want the probability that a mean falls into some kind of interval because I can even get a complete distribution of the mean. And that's because I'm a Bayesian. And Bayesians do probabilistic models and use probabilistic programming.
So I think we have time for one more question. Did you?
Yeah. I wanted to ask two also quick questions.
Yes.
One, is there a reason why, except for simplicity, why you didn't use Markov chains in this example? And second is, if you're only looking for maximum likelihoods in your model, isn't faster to treat it as an optimization problem rather than sampling everything?
Oh, so the first question, well, I will answer the second question, why I was treating this as an optimization problem. It would be easy because these are Gaussians and this is a fairly simple model, but I was trying to show how something like a probabilistic computing system might work, and this was very easy to implement. Of course, you can then go and do some optimizations, create better algorithms underneath. But this is really not that important. This was just showing you how you might do something simple. And the important part is that you can write your model in a very simple way and then use fairly general engine behind that to actually compute values from the model. So in reality, you would be using very complicated algorithms behind that, using Markov chains and things like that. I wasn't doing anything of this here because, my mind would explode, your mind would probably explode. That would be, I can make another talk about that. I can talk for a year about that because the range of algorithms you can get behind that is almost an infinite number. But what's the important point about probabilistic programming is that you just write your model in a very simple way and let the compiler and let the libraries deal with the rest. And they will be using Markov chains, they'll be using a lot of different methods for sampling. Some of them are inspired by physics, some of them are not. We can discuss that a bit later, but yeah, you can do anything behind the scenes. But probabilistic programming is about just writing the program and letting the engine behind that deal with it. Okay, I think it's time to finish, time for a break, so I will take more questions here if you have more questions, or find me around, and thank you.